Hello and welcome to Stat 441 at Virginia Commonwealth University. This is part 2 of the lecture on simple linear regression. So recall we are working with this example where we are trying to come up with a simple linear model to predict the value of compression versus pressure for an insulation material. And these were the 5 observations that were collected. Using this data, we ran regression using R, and this was the output. Our estimated model is y hat equals negative 0.1 plus zero point 0.7 times x. And in the previous lecture, we conducted a hypothesis test for the beta 1, the slope value, and then this was the p-value 3.656 with a p-value of 0.0354. At 0.05 alpha, we rejected the null and we said that the beta 1 value is significant. Now, the next step is to see how strong is the regression model. And for checking that, we will look at two terms. The first one is the coefficient of correlation, and the other is the coefficient of determination. So let's start with the coefficient of correlation. It's denoted by the letter R, and it measures the strength of the linear relation between the two variables x and y. So how strong is the linear relation between the two? So to measure R, what we do is we will have a value close to 1 or negative 1 if it's a strong relation, and the value will be close to 0, we will have a weak relation. So here's what happens. The sign, the negative or the positive sign, basically indicates the direction of the slope. So if we have a positive R, this means that y increases as x increases. It's an upward trend. And if the value of R is negative, it's a negative trend. The absolute value is, if it's close to 1, it's a strong relation. Then in the middle, like 0.5 or 0.6 would be a moderate strength. And then close to 0 will be a weak relation. So let's look at some examples. These graphs will show us how the value of R varies once the points are close to a line or away from the line. So here is the first one. This will have a positive value of R, and this will be a value close to 1. This will be a value of R close to 0. This is value of R negative 1. You can see the negative or the downward trend. This will be R equal exactly 1 because all points fall in the straight line. This one will be R equals negative 1. Again, points exactly on that downward slope line. This here is a quadratic type of model or a quadratic type of data. And here again, the value of R is close to 0 because there is no linear relation in this case. So the value of R basically helps us understand how strong the linear relation is between x and y. Another measure that is used is called the coefficient of determination. And this will basically measure the contribution of x in predicting the y. Okay, and here again, this is how we do it. So this value, the coefficient of determination, it's also called r squared. It's represented by r squared. Technically, it's the square of the coefficient of correlation. So when you're computing it, you can simply square the correlation coefficient. Now, for this, the way we can understand it, it's basically the percent variation in the y data that can be explained by the linear relation between the x and the y. So here are the properties. So r squared is a value between 0 and 1 because r is a value between negative 1 and 1. So because we are squaring this, so our value will be between 0 and 1. Here again, a value close to 0 means it's a weak relation um, a value close to 1 means that it's a strong relation. Here is the interpretation, and this is important because this helps us decide if we want to use this model or not. So let's say r squared is 0.6. That means that the straight line model uh, relating y and x can explain 60% of the variation present in the sample of the y value. So this is like a moderate strength. We can't trust this model too much. If it has a higher r squared value, that's a better model. Okay, so this is where we can find the r squared value for the compression data. R squared is 0.8167. Okay, so 81.67% variation in compression can be explained by the linear model relating the compression and the pressure. Okay, from the SAS output, this is where you can find this value again, 0.8167. Okay. Now the r square value we can work it backwards and use it to find the correlation coefficient. In this case, square root of 0.8167 is 0.9037. So the value of r for our data set is 0.9037. Because it's a upward trend, we have a positive value of r. Okay, again, here's the interpretation for our compression data. So our prediction equation is y hat is negative 0.1 plus 0.7 times x. And the interpretation for that r squared of 0.8167 is that approximately 82% of the sample variation in compression values can be explained by the least squares line. Okay, now it seems to be a pretty strong model. The beta 1 is significant. Then the last thing that we need to check before we can use this model for prediction is to check the assumptions. So there are 4 assumptions that need to be checked. So we'll talk about each one of these, and then we will look at the residual analysis for our compression data. So here is the first assumption. The assumptions are about the residuals. Remember residuals from the last lecture? It's the difference between the observed value and the predicted value. So if you look at the data and then if you superimpose the line on that, it's the vertical distance between each data point and the line. So we have our assumptions for the residuals. The first assumption is that the mean error, again, the residual and error, these are the same term. So the mean of these residuals or the mean error is 0. We will use a graph to check this. It's called a residual plot. And what we are doing is we plot the residuals on the vertical axis and we plot the variable x on the horizontal axis. If we see a pattern, that means the model is misspecified and it will violate the first assumption. On the other hand, if we don't see a pattern, if we see just random points with no trends, then the model is specified correctly. So we are looking for no pattern in the residual plot. So here is an example of a residual plot where the violation, where there is a violation of the assumption. As you can see, this indicates a clear quadratic pattern. That means the linear model is not appropriate and the mean of the residuals is not 0. So the first assumption is violated in this case. Okay. The second assumption is that the errors have a constant variance. Again, we can use the residual plot to check this assumption also. Now in this we are looking for again a strong pattern. Here, as you can see, this one has a specific cone shape. So if you see a cone shape, this is indicating a strong pattern. What we are looking is nothing, no pattern at all. So this again will be indicating a violation of the assumption. This is an example of a violation of the assumption. The third assumption is that the errors are normally distributed. For that, we use the QQ plot. Again, it is generated using one of the softwares. The QQ plot has the theoretical quantiles on the y-axis and the residuals on the x-axis. So if all points fall on this straight line or approximately on this straight line, then the residuals are normal. So this is an example of normal residuals. The last assumption is that the errors are independent of each other. We will not check this specifically, but the assumption here is that the data points are independent of each other. If they are independent, then the errors are independent of each other. So typically, if you have some kind of time-related data, some kind of time series data, then this assumption might be violated. Other than that, usually it should be okay. Okay, so here is the residual plots for the compression example. You can use R to do that. So for doing that, watch the R video, and I have posted the data set and R code for the compression example. You can find this under R videos. Okay, so this is the first plot, the residual plot that we will use to check assumptions 1 and 2. Mean error is 0 and constant variance. So in this, we don't see any specific pattern. So the assumption 1 and 2 are met. This is the third assumption, normal QQ plot. Again, you can see the points are in the straight line. So we assume that the third assumption is good, and again, independent. The last assumption is also good. So assumptions are all met. So now, based on what we have done so far, beta 1 is significant, R squared is pretty high, all the assumptions are met, so we are satisfied that this model that we made describes the relation between the compression of the insulation material and the pressure. So now we are ready to use this model to predict the amount of compression for a particular level of pressure. Okay, so let's say we want to install the insulation in a particular piece of equipment, and we think the pressure will be 40 pounds per square inch. Remember, it was times 10, our original data. So if we want to estimate the mean compression, we will have to plug in X equal 4. Okay, compressive pressure of 40 pounds per square inch. So when we plug in 4, y hat is negative 0.1 plus 0.7 times 4, which is 2.7. So that's a point estimate based on the model. We can also create two intervals around this value, and these two intervals are called the confidence interval for the mean value of y. So basically y hat, which is this value, the estimated value using the model, and then using the distribution of the y hat to come up with the confidence interval for the mean value of y. Again, we will use the software, so you can check the R code for this. We can create another interval, which is the prediction interval, and it's the interval for the individual y. Okay, so this uses the standard deviation of y minus y hat. Anyways, so this is what we can do in R. So we run the linear model, and then we use the code. Again, you can check the video and the code posted. We can create the prediction interval, and then we can also create the confidence interval. So this is the prediction interval from 0.502 to 4.89. This is the confidence interval, which is from 1.64 to 3.76. So these are the interval estimates for our when the pressure is 4 or X is 4. Okay, so our estimated interval is 1.6 to 3.8, so which basically encloses the mean amount of compression when insulation is subjected to a pressure of 40 pounds per square inch. And the other interval is the prediction interval, so which basically means that we predict that the compression for the piece of insulation material will fall between 0.5 and 4.9 inches. Okay, so that's all about regression and the basics of regression. So please watch the R videos, the data set and the code for the compression example. can be used to run all and get the regression output or the graphs for the analysis. Thanks for watching.